I'm Bob Duhamel, and today we are going to practice calculating the impedance of AC circuits where we have a capacitor and an inductor in series. Now, one of the first questions I get asked about these exercises is, do we really need to know this stuff? And the answer is, well, on a day-to-day basis as an electronics technician, probably not. But it's something you do need a basic understanding of, and if you want to become a certified electronics technician, you will probably see problems like these on the certification exam. And if you want to get a general radio telephone operator's license in the US or a equivalent license in another country, you'll almost certainly come across problems like these on those exams. So it's something we do need to become familiar with. Now I'm going to break this up into a number of short videos instead of one long one, so we don't have to worry about having a long attention span. So let's get started by repeating the circuit we used in the previous video and then working off of that one to do some variations. Before I move on, I need to talk about calculators for a moment, because even though the number keys of all calculators are virtually identical, after that no two calculators are the same. And I will be showing the calculator keys as I press them in the rest of this video, so you need to be familiar with your calculator before we move on. The special keys I will be using are store and recall, so we can store a number then recall that later. I will be using the square button and the square root button. I will also be using the arctangent button, and I will be using the reciprocal button. So you need to be familiar with these particular buttons on your particular calculator. So let's begin with the store and recall. On my calculator, I have a key marked STO, and I have another one marked RCL for store and recall. Some calculators may have an MN for memory in, and then an MR for memory recall. But there may be other buttons too, and in fact there may be ways to store multiple numbers. I will just show the word store and recall when I go through the calculations, but you need to know how to do it in your calculator. I will also be using the reciprocal button. On some calculators, the reciprocal button is labeled as 1 over x. I will be using that on the video, but many calculators label the reciprocal button as x to the power of minus 1. So you need to know which of those buttons works on your particular calculator. Another button I will be using is the square button and the square root button. They may be the same button. You may have to press a function key before one of those functions. For example, my calculator has a button labeled for square root, has a square root symbol on it. But to get a square, which is labeled x to the power of 2, I have to press a function key, which is labeled INV on my calculator for inverse. Sometimes it might be labeled FN for function. You might even have multiple function buttons with different colors and have different colored functions on your calculator to know which button to press first. And finally, we are going to use the arctangent button. Your trigonometric functions are labeled as SIN, COS, and TAN for sine, cosine, and tangent. But they will probably also have a label above them labeled SIN to the power of minus 1, COS to the power of minus 1, and TAN to the power of minus 1. And that is your arcsine, your arccosine, and your arctangent. So I will be showing TAN to the power of minus 1 as I go through the calculations, and you will most likely have to press some kind of a function key. In my calculator, I have to press the INV key to get the arctangent function. So become familiar with your calculator. I will show these as I go along, and just make sure that you know how to do the functions on your particular calculator. So that circuit had a source, an AC current source or an AC voltage source, with a frequency of 60 hertz. Being in North America, it's kind of a habit of working with 60 hertz. Other countries tend to use 50 hertz, but we'll work with this. The math is the same. We had a series resistor, an inductor, and a capacitor. The resistor was 30 ohms, the inductor was 100 millihenries, and the capacitor was 100 microfarads. So what we want to do is calculate the impedance of the whole circuit along with the phase angle, and we'll take a look at both polar and rectangular notation for that. So let's just go through the whole calculations again. I'll get my trusty calculator ready so I can punch the numbers in. And so what we need to know is, first, what is the inductive reactance? So how is this inductor going to react to our 60 hertz? And the formula for that is our X sub L equals 2 pi FL. So that's going to be 6.28 times our frequency, 60 hertz, times our inductance, which is 100 millihenries, which is 0.1 Henry, so 0.1. So we just simply do the math there. 6.28 times 60 times 0.1 equals, and we get 37.68 what? Ohms. So our inductive reactance is in ohms, 37.68 ohms. So now we know at 60 hertz, this inductor will have 37.68 ohms of inductive reactance. So it acts sort of like a 37.68 ohm resistor at that frequency. Now we need to calculate the capacitive reactance, which is capacitive reactance is equal to 1 over 2 pi Fc. So that's going to be 6.28 times the frequency, 60 times the capacitance. So that's going to be 6.28 times 60 times 0.0001. So 100 microfarads is 0.0001 farads. And we hit the equals button, but we don't have the answer yet. We have to take the reciprocal. So I take the reciprocal, and we end up with 26.53 ohms. So there we have it, 26.53 ohms for the capacitive reactance. So let's get this clutter off the screen here, off the board, if you will. And so now we've calculated the reactance here and the reactance there. So how do they work together? So remember, by convention, our inductive reactance is positive and our capacitive reactance is negative when we add them together, because since they're 180 degrees out of phase, they simply work opposite to each other. So don't forget that the current through the circuit, this being a series circuit, the current's going to be the same everywhere. So there's no phase angle for the current. That's our base measurement, if you will. So the phase angle of the voltage in the resistor, there is none, because there is no reactance there. So if we increase our current, we increase our voltage, and vice versa. But as the current increases through the inductor, our voltage is 90 degrees out of phase. Remember Eli the Iceman? So our voltage leads our current in an inductor. So the current is the same everywhere. So our voltage comes 90 degrees ahead of the current in the inductor. And in the capacitor, the voltage comes 90 degrees behind the current in the capacitor. So here's the current following the sine wave. The voltage across the inductor is going to be ahead of the current, and the voltage across the capacitor is going to be behind the current, and that's going to be 90 degrees for a total of 180 degrees between the voltage across the inductor and the voltage across the capacitor. So since they're 180 degrees out of phase, what's happening? Here's the voltage across the inductor, there's the voltage across the capacitor, and they're completely countering each other. So we take our inductive reactance, which is going to be proportional to the voltage, and we make that our positive number. We take our capacitive reactance, that's our negative number, and we add them together, and if they are equal, they will completely cancel each other out. But if they're not equal, one's going to be a little more powerful than the other, as we'll see in just a moment. So our inductive reactance and our capacitive reactance are simply subtracted from each other. So let's draw our triangle here, and that's going to be represented by 30 units, which is our resistance. And our inductive reactance is positive, so by convention we go up for the inductive reactance, and that's 37.68 ohms. And then we subtract our capacitive reactance, 26.53, so we just drop that back down there. So we go up 37.68, then back down 26.53, leaving us with a total of 11.15 ohms. And because the inductive reactance was greater than the capacitive reactance, we have inductive reactance left over. So the entire circuit ends up having a total reactance of 11.15 ohms, and that is inductive. So I'll put that as X sub L here. And now our impedance is going to be the hypotenuse of that triangle. How do we calculate that? Remember Pythagorean theorem. So our reactance is 11.15 ohms. We add that to our resistance, which is 30 ohms, and we square those and then take the square root. And that's going to give us the length of the hypotenuse. So that's going to be 11.15. We'll square that and store it away. And then we're going to add the square of our resistance. So that's going to be 30 squared. Add that to our total reactance squared. And then take the square root. And we end up with 32 ohms of impedance. So the length of this line is going to be 32 units. So 30 ohms of resistance and 11.15 ohms of reactance gives us a total impedance of 32 ohms, but we also want to know what the phase angle is. So let's start drawing this out here. Our impedance is going to be 32 ohms with a phase angle of whatever that is. What's it look like? Not much, maybe around 10 degrees at the most. Well, we calculate that out by taking the reactance, divide that by the resistance, and then we take the arc tangent of that, which is going to be, on many calculators, that's going to be the tangent button to the power of -1. Depends on your calculator. Some say arc tangent, some say tangent to the power of -1. So that's going to be 11.15 divided by 30, and then take the arc tangent of the result. So here we go, 11.15 divided by 30 gives us a number. That's just an intermediary number. I take the arc tangent of that, and I got 20.38 degrees. So it's going to be 20.38 degrees, and it's going to be positive because, by convention, if our angle goes this way, it's positive. If it goes that way, it's negative because of our inductive reactance being positive and our capacitive reactance being negative. So there is the total result. Erase our clutter here. So at 60 hertz with 30 ohms, 100 millihenries, and 100 microfarads, we have 37.68 ohms of inductive reactance, 26.53 ohms of capacitive reactance. Subtract our capacitive reactance from our inductive reactance to find our total reactance, which turned out to be a positive 11.15, meaning that it is inductive. Pythagorean theorem to find out the length of the hypotenuse, which gives us our impedance, 32 ohms. Then divide our reactance into our resistance, take the arc tangent of that to get the phase angle. And once again, to put this in rectangular notation, is going to be the resistance and then plus or minus J. In this case, since it's inductive reactance, it's going to be plus J. And then the reactance. So there's the impedance in polar notation, 32 ohms with a phase angle of 20.38 degrees. There's the impedance in rectangular notation, 30 plus J, 11.15. Now, remember, this is a complex number. In standard mathematics, that would be an I. We use the J in electronics because the lowercase I is alternating current. And so we just use a J instead of an I. So complex number representing simply a resistance. Make a right angle turn to the left or to the right, depending on positive to the left, negative to the right, describing this triangle in two different ways. So there's the problem we did before. Gives us a starting point to do the next problem. So what happens if we make a change to this circuit? I'm just going to change the frequency and see what happens. Let's get rid of our numbers. So let's change this to, let's double it, 120 hertz. So what's going to happen? Well, I'm going to go through the calculations, but we could fake it because this was 37.68 ohms. This was 26.53 ohms. What's going to happen to our inductive reactance when the frequency goes up? Let's draw a little quick plot here. Here's our frequency, and here's our reactance. Inductive reactance is going to go up with frequency, but capacitive reactance is going to go down with frequency. So if we double the frequency, our inductive reactance is going to go up. How much? It's going to double. I'm going to redo the calculation for practice, but double the frequency, our inductive reactance doubles. What's going to happen if we double the frequency with our capacitive reactance? Well, frequency goes up, capacitive reactance goes down. So if we double the frequency, this should cut in half. So this will double to 75.36 ohms, and this will cut in half to 13.26 ohms. Let's do the calculation and see if that comes out right. So let's leave those up there just to see if our numbers come out as we expect. So we have 100 millihenries and 120 hertz. So what's the formula? X sub L equals 2 pi FL. So that's going to be 6.28 times 120 times 0.1. Let's do the calculation. 6.28 times 120 times 0.1 equals 75.36. Now let's do the capacitive reactance. That's going to be capacitive reactance, let's write it here, is equal to 1 over 2 pi FC. So that's going to be 6.28 times 120 times 0.0001. And then take the reciprocal of that, so 6.28 times 120 times 0.0001 equals, now I take the reciprocal, and I get 13.26, which I'll circle right there. So we did the calculation and we got the same numbers we expected. So double the frequency, we double our inductive reactance. Double the frequency, we cut our capacitive reactance in half. So now that we have those numbers, let's do the rest of the calculation. What is the total impedance? So draw our triangle here, and we're going to add 75.36 ohms, so that's going to be way up there. 75.36, and then we are going to subtract 13.26. So what's the number going to be? 75.36 minus 13.26 equals a total of 62.1 ohms. So now that we've doubled our frequency, we went from a reactance of 11.15 ohms positive, meaning inductive, to 62.1 ohms positive. So now we have, well, let's draw this correctly. Now, of course, my angles are not perfect here because I'm just drawing them by eyeball, but the numbers will be correct. So we have a total of 62.1 ohms of reactance, and it's positive. So that's going to be 62.1 ohms of inductive reactance left over. This is still going to be 30 ohms. So what is the hypotenuse of that triangle? It's going to be 30 squared plus 62.1 squared. And take the square root of that. So take 30, square it, store it in memory. That comes out to 900, as if that matters. Now we're going to add that to 62.1 squared. So 62.1 squared. Add that to the previous one, and I get a number. I'm not worried about that yet because I need to take the square root of that. And I got a total impedance of 68.96 or 60, let's just call it 69 ohms. Get this out of the way here, getting a little cluttered. So our hypotenuse was 69, so we have 69 ohms. What is the phase angle? That's going to be x divided by r. Take the arctangent of that, so draw that up here, which is going to be the arctangent of 62.1 divided by 30. So 62.1 divided by 30 equals, I don't care what that number is, but I take the arctangent of it, and I get an angle of 64.2. So there is the same problem with doubling the frequency. So we ended up with 75.36 ohms of inductive reactance, subtracted 13.26 ohms to leave us with 62.1 ohms. Draw the hypotenuse of that triangle. use the Pythagorean theorem. 30 squared plus 62.1 squared, take the square root, gave us 69 ohms for the length of that. And then the angle was going to be x over r, arctangent of x over r. So 62.1 divided by 30, take the arctangent, gave us 64.2 degrees. So write this out in polar notation, is going to be 69 ohms with a phase angle of 64.2 degrees, positive. And what's that going to be in polar notation? Still 30 ohms. And it's positive reactance, so it's going to be plus J, what's this number? 62.1. So there's the impedance of the same circuit if we doubled the frequency. Now let's do this one more time, cutting that frequency in half. Get the clutter out of the way, and let's see what happens. So now this is going to be 30 hertz. So let's do the calculations. I'm going to write them up each time to remind you of the formulas as we go over it, because what is this? This is practice. So we have 100 millihenries and 100 microfarads, but now we have 30 hertz. So the inductive reactance, X sub L, is going to equal 2 pi FL. So that's going to be, which equals 6.28 times what? 30. And we're still times 0.1. So the inductive reactance is going to be 6.28 times 30 times 0.1 equals, and we got 18.84 ohms of inductive reactance. What's going to happen to the capacitive reactance? The inductive reactance went down, but as frequency goes down, the capacitive reactance goes up. We have our capacitive reactance, X sub C equals 1 over 2 pi FC, which equals 1 over 6.28 times 30 times 0.0001. So here we go. 6.28 times 30 times 0.0001 equals, take the reciprocal, and I got 53.07. So now our capacitive reactance is greater than our inductive reactance. Let's draw that out. Here's our triangle with our 30 ohms. And now we add 18, right about there you think, 18.84 ohms of inductive reactance, positive, but now we subtract 53.07. So we subtract 53.07, we now end up with a negative reactance. So that's going to be a total of 53.07, giving us, well, let's go 18.84 minus 53.07 equals minus 34.23. So our actual reactance is going to be now capacitive because we ended up with a negative number, and by convention we go down. And so now our triangle looks like that. Let's erase our now negated inductive reactance. So there we have now 30 ohms and negative 34.23. So to find the total impedance, how do we do that? Pythagorean theorem. So we have 30 squared again, plus, now we don't work this as a negative number. We just take the absolute number here with no sign. So that's going to be 34.23 squared. Take the square root of that. So 30 squared. And we're going to take 34.23 squared. And we add them together. I don't worry about the number I get there, but then I take the square root, and I got 45.51. So our impedance is 45.51. What's the phase angle? Once again, we use absolute numbers. That's going to be 34.23 divided by 30. Let's put the formula up here again. So our phase angle is equal to the arctangent of x over r. So x is 34.23, our capacitive reactance now. So that's 34.23 divided by 30 gives us a number. It's 1.141, but who cares about that? We want the arctangent of that, which gives us a phase angle of 48 degrees. This is not a very well drawn triangle here. So it's 30 ohms of resistance. Put that up there. And the phase angle was 48.76. Like I said, I'm not drawing these very well because I'm eyeballing them, but obviously it's a much steeper angle than that. So if we redraw it more correctly, it might look something more like that. Does that look better? There we go. So our triangle looks more like that. So we have a impedance of 45.51 ohms with a phase angle of 48.76 degrees. So let's draw that notation up here. 45.51 ohms with a phase angle of 48.76 degrees. And that phase angle is negative because it went down. And if we want to use rectangular notation, once again, it's 30 ohms. And this time it's minus J because we make a right turn instead of a left turn. Minus J, 34.23. And so there's rectangular notation and there is polar notation. And I'm going to stop here. I said I'm going to make some shorter videos. So what we did is we took our original problem and we doubled the frequency, then cut the frequency in half, recalculated it, and found out what our impedance was in polar notation and in rectangular notation. And I'm going to make another video where I change the numbers around a little more, so stay tuned for that. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.